No, we're video camera. Pretty good. Be like the framing like correct? Ish?
Yeah.
Okay.
It's a bit zoomed out. Yeah.
For like emergency, you can go. I'm gonna take it. Alright, so yesterday we ended with talking about models, and we were talking about the relationship between hyperbolic and Euclidean geometry, and I started giving this silly example. Who's having a pool party? Oh, it was Guang, right? Yeah, Guang was having a pool party, and he got to the pool, and unfortunately, just before everyone arrived, he noticed that the pool had some pool rules. And the first rule at the pool was like no. What was it? The first rule? No running. No running. Okay. And so yeah. So no running. So that means that then that's pretty sad because Guam was planning on having an all-running pool party, and now he cannot. So any running pool party that Guam was planning on having now like violates this rule, and so it's not allowed. Okay, and then we can have more rules, like no dogs, no dogs. So that's like a pretty reasonable rule to have at a pool. And so that sucks though, because Guang was going to have an all-running, all-dogs party.
All of his members are dogs.
And and now he can't do that. So every time, are you guys feeling this? Every time you add another rule, you restrict Guang's freedom to have the party that he wants to have, and when you add these new rules, you restrict the number of possible parties which are going to be able to meet all these rules. And if we keep going, wait, I had a couple more from last period. I can't remember. No running, no diving. That's like a rule sometimes. Maybe like no skateboards.
What?
That was a big issue in my trashy town of New Jersey. The ongoing war between the people who wanted to skateboard in peace and the man who wanted to stop all skateboarding from happening everywhere. So, all right. So we have these now. We have these rules now, right? And these are basically like axioms, and they're axioms which restrict the number of possible pool parties. So we see that the models get smaller as we add more and more rules. Everyone cool? And by the way, from these axioms, you could produce theorems. Someone give me a theorem that would hold based on these four postulates about the pool party.
You cannot have a dog diving into the pool on a skateboard after it was running.
Yeah, so that's right. If there's no running, then there can't be any running dogs. That's like a theorem. And there can't be any diving dogs, and there can't be any skateboarding dogs, and there can't be any running, diving, skateboarding dogs, etc., right? You can't do like a jumping off of a skateboard into a dive trick. You know, there's many things you can't do. So from a set of rules, they can just go longer and longer. You can prove certain things. So you know more about the kind of party that's happening, the more rules you have. Is everyone following? Okay, and now there are two sort of extreme cases. One extreme case was Guang's initial suggestion of having a party with no rules. Yeah. All right, so that's like the that's like just anarchy, right? Now if we have no rules, anything is allowed. But of course, if anything is allowed, we can say almost nothing about it. So, and the other extreme might be that you have so many rules, and I mean, sometimes the pool rules are quite long, you know, like 20, 30 rules long. What if every generation people keep adding more and more rules to the list of things you're not allowed to do or you have to do at a pool?
It's like the U.S. Congress.
It's like the U.S. Congress. Yeah, that's right, Como. It's estimated that there are like so many laws that it's basically impossible for you to ever even know what they all are. Like if you just started reading all the laws when you were 14, you wouldn't like finish reading them even before until you were just like dead. All the federal laws, state laws, it's completely out of control. Probably like they estimate, like people like experts estimate that the average American is just breaking just like hundreds of laws like per day. There's really just nothing you can do about it. I think that's hyperbole?
Yeah.
No, if you include like traffic things.
Okay, things with traffic laws.
And also it's violations of zoning. You put a poster up on your wall and you. Yeah. Okay, anyway. I have a contraband air conditioner in here. I'm above average. Okay. Good. So what if you add so many? Okay, first, this is important. This is now we're not just screwing around. This is math. What if you added so many rules and so many rules and so many rules? What if you got down to like rule 101,082, and that rule was like dogs must be in the pool. Okay, can someone explain to me? Yeah, that is a contradiction. So what kind of party, if you're going to have a party that satisfies all of these rules, or if you want a party that satisfies all these rules, you actually just can't do it, right?
Yeah.
This is
If you just didn't have dogs.
Well, if you just had no dogs. No, dogs must be in the pool, not dogs if they're present. Just straight up dogs must be in the pool. You cannot have a party unless there are dogs in the
Not
pool.
every dog, but there must be
Yeah.
dogs in the pool.
Yeah, so, alright, yeah, dogs have to be in the pool and all that. Wait. Staying kind of focused here. So, yeah, this is the other extreme. If you add every time you add an axiom, this is deep. Every time you add an axiom, you now restrict the possible ways in which that world could look if it satisfies those axioms. And if you keep adding more axioms and keep adding more axioms and keep adding more axioms, you now know more and more about what that party looks like. You know more and more about your geometry. But the number of possible geometries gets smaller. And if you add so many rules that in fact two of your rules contradict each other, then in fact no possible pool party can satisfy all of these rules. All right, and we could imagine this going back to like the real subject of this class, geometry. You could imagine in some years on this presentation, we created a thing called stupid geometry. And here's how stupid geometry goes. Axiom 1, through every 2 points there's a line. Axiom 2, you can extend lines indefinitely or whatever. 3 is like the one about the circles. 4, all right angles are congruent. And then maybe like axiom 5, no right angles are congruent. Alright, talk to me about stupid geometry.
You can prove whatever you want.
Yeah, it's terrible, right? It's bad, because we now have 2 axioms which are in fact just contradict each other. And so you can come up with, nothing prevents one from having an axiom system like this, but if you do it, then you just can't have any model which satisfies the axioms. The axioms are actually contradictory. That's really bad, because it means you're just doing nothing. And in fact, like Sahil says, from contradictory premises in classical logic, you can prove anything. That's a principle of explosion. So with axioms 4 and 5, I can prove any exotic thing whatsoever about this geometry. Alternatively, going from the other perspective, you could have just have the geometry called like no geometry. Ready? Here are the axioms. I'm done. There were no axioms. Okay? So yeah. So this is not much of a system, because now with no axioms I can say nothing, I can know nothing, I have no theorems, I have no actual knowledge, and I have no
Yeah, we can use whatever model we want.
Okay, yeah, and you can use whatever model you want, so there are just no rules. So alright, so it seems ridiculous that you would have now this dogs in the pool, no dogs in the pool, or I guess the other way around, axioms are obviously contradictory. But of course, like contradiction doesn't just mean that you have 2 axioms which are contradict each other directly. It could be that the contradiction emerges via some sort of very long chain of like logic, right? It might be, yeah, so similarly, have you considered that possibly Euclidean geometry is just inconsistent? None of the 5 axioms of Euclidean geometry appear to be contradicting each other, but then again, you have to do all the work, and by all the work I mean all the work. You have to prove every conceivable thing that can come out of these postulates. So Euclid did like a lot. So he books like 1 through 13, and he's improving things, all from these postulates. But like, how about the unpublished works of Euclid that no one likes to talk about? Book 17 or so, somewhere down towards the end of book 17. This is just a joke. He just has suddenly a contradiction just emerges. Just a straight up contradiction. It's not impossible that in fact the very axioms of Euclidean geometry just lead to a contradiction if you follow them far enough. Alright, speaking from the perspective of an ancient Greek, why do you think this is extremely unlikely, bordering on impossible?
Because the real world is not a contradiction, and Euclid is about the real world.
Yeah, maybe that's a good answer, right? The postulates of Euclidean geometry to an ancient Greek are just true. And you can't get a contradiction out of truth, right? But from a modern perspective, perhaps, where, okay, now it's the 19th century, we had Protestantism, we had, wars, we found weird people all over the world doing different things, cannibals, people from China, now we're all atheists, no one believes anything anymore. Perhaps now we no longer believe in these kind of archaic notions like truth. Maybe now we just have some axioms and we're not going to say whether they're true or not. Could there be an axiom, contradiction built into Euclidean geometry? Yeah, maybe. Maybe. Okay. Good. Do I have anything else to say about this? No. All right. So that's pretty important to show that your axiom. That's a kind of a question that didn't emerge until more modern times. Is this pressure to actually show that your axioms are even possible? That it is even possible to satisfy all of them at once. All right. Take back over.
You do need.
So we're basically, I think that, yeah, okay, so this is just like going back to the set diagram we had before of like, in terms of theorems, Euclidean geometry encompasses neutral geometry, but in terms of models, neutral geometry encompasses Euclidean geometry. And I don't think we really need to get into that again. So, this is back to what Rose said, is Euclidean geometry consistent, and how can we prove it? The answer is like, I don't know. It's like, yeah. I don't know any of this. Yeah.
Yeah, that's it. That's our answer. The answer is I have no idea how to do this. And no one was really trying to do it until suddenly they started worrying and maybe then they started trying. But that's for a later lecture.
Question. Read it.
Okay.
Yeah, what if you don't think the parallel postulate can be proven from the other four postulates?
Yeah, so transition, right? Suppose you've spent your entire life trying to prove the parallel postulate from the other four. And by the way, like a whole bunch of thousands of other people also spent their entire life doing it. And also this has been going on for 2,000 years. You might start to think that maybe it can't be done. And if you think it can't be done, then what next?
Try to prove it can't be done.
Yeah, Dylan, say that again.
You try to prove that you can't prove it from the other.
Yeah, man, if you've been trying for 2,000 years to prove the parallel postulate from the other four, this is getting deep now, and you're unsuccessful, and you're pretty smart, then maybe you start thinking, maybe you start believing that the fifth postulate can't be proven from the other four. And if that's what you think, then that itself should be provable. How can you prove that you can't prove the parallel postulate from the other four? And basically you'd be proving that all these people for 2,000 years have been wasting their time.
Yes, so all these people for 2,000 years, Lydia.
I don't know what that means. Yeah, wait, oh, you were
We had a
supposed to do
discussion
it?
after class, yeah.
Wait, there was supposed to be discussion. Well, how do you do it?
Try it without it.
Try it without it. It's like this is an actual question I'm asking you right now. How do you prove that you can't prove the fifth postulate from the first four postulates?
I guess you could prove that the fifth postulate is, say, equal to A and B, and prove, no, because then it just reduces, you'd have to prove that some other thing is improvable. I don't really know.
You could just assume the fifth is not true and then
I'm not talking about prove it. Okay, so we're not talking about truth anymore. We're just talking about, can you prove the fifth postulate from the first four, or can't you?
there's no way.
People thought you could, and they tried to prove it from the other four, and they didn't get anywhere. Or they got somewhere, but they weren't successful. What if you think that they weren't successful just because of lack of effort or ingenuity, but in fact they were unsuccessful because it's just impossible? Turn the camera when we move that. If you think it's just impossible to prove the fifth postulate from the other four, then
Is that like
what do we
on
do?
a
How do we prove
Can you
that?
adjust this to make sure it's pointing there?
Oh, no one knows. Come on.
If you assume that the fifth postulate isn't true, and then you find that you can, and then if you're able to prove that you still have a consistent geometry, then you could say that the fifth postulate can't be proved from the other four, because if it could be, then you'd have a contradiction, and then the other one would not be.
Yeah, okay, that's pretty good. Yeah, that's actually pretty close to the answer. Although it's sort of, it's hard to show that, yeah, okay, yeah, good. All right, so wait, once you hear this, it's like so obvious, you'll never imagine that you didn't know this. Sahil, take it away.
Yeah, so basically, going off what Troy said, you have to make a model where the fifth postulate does not hold. Well, like it is where the fifth postulate is false, and then if that model is consistent, then you can't prove the fifth postulate using one of the first four.
This is what models are good for. A model is just an example. If you think the fifth postulate can't be proved from the other four, you just come up with an example of a world in which the first four postulates are true and the fifth one is false. It's just like, suppose someone thought that you could prove no skateboards from no running, no dogs, and no diving, right? And you're like, no, I don't think you can. How would you prove to someone that the no skateboards proposition cannot be proved from the no running, no dogs, no diving proposition?
Have some guy come in with a skateboard and then not run.
No, wait, other way around. To show that I can't prove no skateboards from the others. Wait, maybe I cut you off.
Yeah.
He was right?
Yeah.
Okay, sorry. Say it again.
Double negative.
Okay.
Have some guy come in with a skateboard and then not break any of the first three rules.
Yeah. Basically, just make a party in which there is no running, so you're following rule 1, and there are no dogs, and there is no diving, and yet there are no skateboards. No, there are skateboards. Yeah, it's weird because there are some double negatives. Yeah, it's like if you just, it's like, okay, yeah, good. So yeah, to show that yeah, good.
Yeah, it's just, so how, yeah, so let's say that we wanted to make a model. What would the model entail? What would it mean for the fifth postulate to be false? There are really two options we can go with this. We're using Playfair's axiom, by the way. So if you want to contradict Playfair's axiom that there's only one, if you have a point in a line, there's only one line parallel to through the point parallel to the original line. So you could contradict that either by saying that there are no lines, or that there are multiple lines, each of which is parallel to the original line. So those are basically the two ways to go about proving that.
Okay.
So
So that was the long philosophical intro that took like a period and a half. Now we're getting to actually like what happened.
Yeah. So like now we're getting to like real geometry, which is like weird. Even height can't pronounce things. So yeah, attempted to prove the parallel postulate by contradiction. I mentioned earlier, you assume the fifth is false, then try to show that there is no model, basically, and so that it's possible for that to work. Let's see.
the Lambert quadrilateral is
Oh yeah.
it's kind of weird. It's basically a quadrilateral where three angles are right, but so like this. But it makes no statement as to the angle of as to the value of the fourth angle. So
That's called a Lambert quadrilateral.
yeah, there is another quadrilateral that we'll go into a bit more detail on later. Omar Khayyam, he wasn't trying to prove the parallel postulate. He was trying to show that it was equivalent to some other thing he had, but I don't really understand what that is. Just like two lines that converge can't diverge, and I don't really understand the meaning
it kind of
of
makes
that
some sense, right? He's sort of saying that two lines, if the distance between two lines is getting smaller, or something like that. That's my interpretation.
But yeah, I mean that makes sense. But when I read it, it said that for two intersecting lines, and that just didn't make any sense.
Okay, I'm not sure.
Yeah.
I thought I once knew this, but I don't remember. But yeah, I thought it was something like if two lines are getting closer to each other, then they have to intersect.
Very simple.
And if And something like if they're getting closer to each other, then they don't start getting farther away from each other later.
So like this isn't possible, kind of, except
Right.
it's described in a really weird way.
Yeah, but actually, if that's not possible, then that is equivalent to the parallel postulate.
Yeah.
We will find. Yeah. Okay. All right. Keep going.
And now for Morris Klein's favorite mathematician, Security. So, we hopefully all read about this in Laws of Certainty.
Oh, of course.
So Security went through both assumptions of that the fifth postulate is false, and he tried to prove a contradiction. So when he assumed that the sum of the angles in a triangle, well, when he assumed that there are no lines through a point parallel to a given line, which is equivalent to that, equivalent to the sum of angles in a triangle is greater than 180 degrees, then he got a contradiction, which we know he did, because we already proved that the sum of angles in a triangle is no greater than 180 degrees. But then when he assumed that the sum of angles in a triangle was less than 180 degrees, he didn't really get a contradiction. He thought he did, but that was just like really weird results, but nothing that actually contradicted.
So it's basically you get this, which is less than 180 degrees, and you say, you know what, this looks weird, I don't want it to be real, so it's definitely a contradiction.
Yeah. So does everyone understand his approach? This was one of the questions, right? Like what did Sakari do? Well, first of all, he's trying to prove the parallel postulate. He's trying to prove it that it relies on the other four. So he assumes neutral geometry, and then he just assumes the opposite of the fifth. And if he can take the opposite of the fifth and get a contradiction, then the fifth must be provable, right? It's just like a straight up fish proof. Take 1 through 4 as your premises, assume not 5, get a contradiction, therefore 5, and we're done. So it's done in cases, right? Because either take a triangle, either it has 180 degrees, greater than 180 or less than 180. If it has an equal to 180, then I've proven the parallel postulate, because I can prove the parallel postulate easily from the triangle having 180 degrees. If we suppose that the triangle is greater than 180 degrees, that's the exact proof we did on the board, right? We said we started with the triangle with 180 plus p, and we got something that just contradicted neutral geometry, so that's impossible. And then the other option, that the sum of the angles is less than 180, just led him to just he just created this just world of just grotesque figures that he just found to be repulsive, or something, and he never quite got a contradiction, but he just sort of said, well, this is just all wrong. This is just clearly all wrong. So he gives up.
So these are the quadrilaterals that we get into more detail. They're generally called Sakari quadrilaterals, but since Khayyam got it 500 years before him, I wanted to, well, not I want to, it's actually also an accepted name. But yeah, so it's a triangle where it's a quadrilateral which has 2 right angles, and well, like this. So you have your 2 right angles, and then these 2 sides are congruent. And then the question is about the angles to the 4th side. And in Euclidean geometry, which we should know, they're both right angles, because yeah, it's a square. Well, rectangle. In hyperbolic geometry, which is equivalent to the one the weird triangle that Artemis had, the summit angles are less than 180. The sum of the summit angles are less than 180 degrees, which kind of makes sense, right? If the triangle has less than 180 degrees, then a quadrilateral would have less than 360. And then the third type is where the angles at the top are more than 180 degrees, which comes from the assumption that there are more than 180 degrees in a triangle. And that's for a certain type of geometry called elliptic geometry. So Johann Lambert, he was a bit like Sakari in that he tried to prove the 5th postulate, but he didn't just give up when he found that something was really weird. He kept going through the hyperbolic geometry, and he didn't get any contradiction. So when he realized that, he thought that this geometry might be logically consistent with itself, and just as consistent as Euclidean geometry is. So then, what is true?
Wait, how do you pronounce that?
Boyai.
Boyai. So, there was Wolfgang and his son Janos. And so Wolfgang spent his life trying to prove the parallel postulate in the same sort of assuming that a triangle has less than 180 degree way and using hyperbolic geometry, trying to prove that wasn't real. Then Janos later, after his father warned him not to, found that the parallel postulate is independent of the first four, so like hyperbolic geometry does exist. Wolfgang sent the work to Gauss, and Gauss is an interesting response for that.
Yeah, so Gauss, I mean, you guys know Gauss, like one of the, whatever, 3 greatest mathematicians of all time or something?
Who are the other two?
Possibly, I don't know.
Euler, probably?
Be vague. Yeah, maybe like Gauss, Euler, and like, I don't know. So, incredibly influential. He's, at the time, he's the greatest living mathematician, and he's a total jerk. Basically, no one likes him, and he has only one friend in the entire world, which is this guy he was like friends with from childhood, which is Wolfgang Bolyai, who spends his whole life trying to prove the parallel postulate. And yeah, okay, well, we'll see. Let's see, we have who's going to read the quotes?
You must not attempt this approach to parallels.
So wait, this is the letter. This is Wolfgang's letter to his son Janos.
Yeah, when Janos was just like, hey, I'm going to do math, Wolfgang just, don't do this. You must not attempt this approach to parallels, for I know this way to its bitter end. I have traversed this bottomless night, which extinguished all light and joy of my life. I entreat you, leave the science of parallels alone. I thought I would sacrifice myself for the sake of truth. I was ready to become a martyr who would remove the flaw from geometry and return it purified to mankind. I accomplished monstrous, enormous labors. My creations are far better than those of any other, and yet I have not achieved complete satisfaction. For here it is true that if it's failed to make the grade, even by a smidgen, it might as well be the worst. I turned back when I saw that no man can reach the bottom of this night. I turned back unconsoled, pitying myself and all mankind.
Hold on, continue.
I admit that I expect little from the deviation of your lines. It seems to me that I have been in these regions, that I have traveled past all the reefs of this infernal Dead Sea, and have always come back with my broken mast and torn sail. The ruin of my disposition and my fall date back to this time. I thoughtlessly risked my life and happiness, either Caesar or nothing.
Oh.
For God's sake, I beseech you, give it up! Fear it no less than sensual passions, because it too may take all your time and deprive you of your health, peace of mind, and happiness in life.
Okay. Nonetheless.
And wait, there's more.
Oh yeah, no, Janos persists. Okay, new dramatic reader. Swap.
I resolved to publish the work on pillows as soon as I can put it in order, complete it, and the opportunity arises. I have not yet made the discovery, but the passage I have was almost certain to lead you to my goal. Provided it is possible, I do not yet yet have it, but I have found things so magnificent I was astounded. It would be an eternal pity for these things were lost to you, my dear father, and bound to remain when you see them. All I can say now is that I have created a new and different world out of nothing. All that I have sent you thus far is like a house of cards compared with a tower.
Yeah, and this is kind of one of these really famous lines in the history of mathematics. Janos, who is considered like the discoverer of non-Euclidean geometry, in addition to one other guy, when he creates this, he assumes the negation of the parallel postulate. He gets these kind of grotesque figures just like Sakari, just like Lambert did, but he sort of further studies and finds that in fact actually this all sort of holds together, and what we have here is an entirely new system of these strange and obscure objects. He writes effectively like an entire other book of the elements now, but based on the negation of the fifth postulate instead of the fifth postulate. And he writes to his father, I have created a new and different world out of nothing. It's kind of like amazing. Yeah.
And then Gauss.
Our our
Basic-
resident asshole.
Basically, yeah.
Yeah, basically, most of this is just like.
No, this is good. This is good. So,
No,
so
but the main thing is.
Wolfgang-
just, like, the italicized.
Wolfgang writes. I'll do this one. Wolfgang writes. He shows.
Turn the camera.
He shows the what his son Janos has made to Gauss, greatest living mathematician, who happens to be his only friend. And Gauss says, if I commenced by saying that I am unable to praise this work, you would certainly be surprised for a moment. But I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he is led, coincide almost entirely with my meditations, which have occupied my mind partly for the last 30 or 35 years. So I remained quite stupefied. So far as my own work is concerned, of which up till now I have put little on paper, my intention was not to let it be published during my lifetime. I have found very few people who can regard with any special interest what I communicated to them on this subject. It was my idea to write down all this later so that at least it should not perish with me. It is therefore a pleasant surprise for me that I am spared this trouble, and I am very glad that it is just the son of my old friend who takes the precedence of me in such a remarkable manner. Ouch! That's like so bad. His basic response is, oh yes, I did all of this 30 or 35 years ago. All in my head, mind you. Oh, I didn't write any of it down, and I didn't publish it, and I wasn't intending to publish it, but I thought I might die soon, so I better write it all down quick before I die, so this knowledge is not like lost to the world. And thanks, you've spared me the effort of having to put the work in to write it all down. Good job. I think that's hilarious. Apparently Gauss did this kind of thing a lot, where he was just ridiculously prolific. He would think about things all the time, and he would publish as much as he could, but some of it he just wouldn't publish because he's just like, I don't care or whatever. And other people would publish things and he'd be like, oh yes. Oh, I did that the method of least squares, yeah, I did that 10 years ago. Here, I have it in this unpublished journal of mine. And he did this like over and over again. People hated him. He never, Wolfgang Bolyai never spoke to Gauss again, and Janos never published again. He sent his work to Wolfgang Bolyai, and Wolfgang was publishing a textbook on geometry, and as an appendix to this geometry textbook, he added in like a 60-page thing about non-Euclidean geometry, and that was the only thing he ever published again. He retired as a mathematician. He was so offended by his dad's best friend. Sad and hilarious story in the history of math. All right, more. All right, that was the historical interlude of how it all happened. Now we're getting down to the actual math. How much time do you have left? Like 12 minutes?
Yeah.
All right, good.
Okay, so hyperbolic geometry. It consists of neutral geometry plus postulate 5 prime, which is using Playfair's axiom again. This is a thing, and both of these two lines are parallel to this one. So the real question for this is whether there is a model that satisfies it. And well, here's one: the Beltrami-Klein model.
So